Act 1. The Mission.
Somewhere above you, right now, at this very moment, there is a telescope. It is not orbiting the Earth the way most satellites do, looping around us every 90 minutes, close enough that you might spot it as a moving star on a clear night. No. This telescope has traveled much, much farther than that. It sits roughly 1.5 million kilometers away at a gravitational resting point where the pull of the Earth and the pull of the Sun balance each other so perfectly that the telescope can remain almost perfectly still, hovering quietly in the dark. It does not need to fight to hold its position. It simply stays. And from there, it watches. This is the James Webb Space Telescope, and tonight we're going to spend some time with it, learning what it is, how it came to be, and what it has shown us about the universe we live in. There's no rush, know where you need to be. Just let the words wash over you, and if sleep finds you somewhere in the middle of all of this, that's perfectly all right. The telescope will still be out there when you wake up. It's not going anywhere. Let's begin at the beginning. Not the beginning of the telescope itself, but the beginning of everything. The James Webb Space Telescope was built, in large part, to look back in time, to witness what astronomers call the cosmic dawn. This is the period, roughly 100 to 500 million years after the Big Bang, when the very first stars and the very first galaxies began to form in an otherwise dark and featureless universe. Think about what that means for a moment. Before those first stars ignited, the universe was not simply dark the way a room is dark when you turn off the lights. It was dark in a more profound and complete sense, a darkness that had never known light. There were no stars to cast shadows, no planets to reflect warmth, no surfaces of any kind for light to fall upon, just vast clouds of hydrogen and helium gas, slowly, imperceptibly drifting together under the gentle but relentless force of gravity. And then, over enormous stretches of time, millions upon millions of years, those clouds grew denser. They collapsed inward, and at their cores, pressure and heat built to such extraordinary levels that atoms began to fuse together. Hydrogen became helium, energy was released, and for the first time in the history of the universe, there was light, the cosmic dawn. No human eye was there to see it. No consciousness existed anywhere in the universe to register that first glow. It happened in silence and in isolation, witnessed by nothing, recorded by nothing, except by the light itself, which has been traveling through the expanding universe ever since. And here is the extraordinary thing. That light still exists. It has been traveling for over 13 billion years. It is ancient beyond imagination, stretched and reddened by the expansion of space itself, pushed out of the visible spectrum and into the infrared, the kind of light our eyes cannot see, but that Webb's instruments are perfectly designed to detect. When the James Webb Space Telescope points itself at a patch of seemingly empty sky, a patch so small it would be covered by a grain of sand held at arm's length, and opens its sensors for hours or even days at a time, it is not merely taking a photograph. It is reaching back through time. The light arriving at its mirrors left its source before our sun existed, before the Earth existed, before any of the atoms in your body had been forged in a stellar furnace and scattered across space. Webb was built to catch that light, to bring the cosmic dawn into focus for the first time, to let us see, however faintly, however distantly, the moment when the universe first turned on. That is why it exists. Breathe in. Let that settle for a moment. We are a civilization on a small rocky planet, orbiting an ordinary star, in a galaxy that contains hundreds of billions of other stars. And yet, we have built a machine capable of seeing the first light that ever existed. That is not a small thing. That is, perhaps, one of the most remarkable things our species has ever done. The James Webb Space Telescope is the largest space telescope humanity has ever launched. Its primary mirror, the great golden structure that collects and focuses light, stretches 6.5 meters across. That is roughly the width of a large living room, or, if you prefer, about the height of a two-story building, laid on its side. To put that in context, the Hubble Space Telescope, which has been orbiting the Earth since 1990, and which has given us some of the most iconic images in the history of science, has a primary mirror just under 2.5 meters in diameter. Hubble's mirror is extraordinary, but Webb's mirror is more than 6 times larger in collecting area, 6 times more surface gathering light from the darkness. And yet, Webb was not designed to replace Hubble. It was designed to extend what Hubble started, to carry the mission forward, to go deeper, to see older, to answer questions that Hubble's incredible work has raised but could not itself answer. The relationship between the two telescopes is something like that between generations. Hubble opened a door. It revealed galaxies forming and colliding, gave us deep field images showing thousands upon thousands of galaxies in a single frame, showed us stars being born inside great pillars of gas and dust. It changed how we understood the cosmos. It changed how we understood ourselves. But every discovery Hubble made carried with it new questions. Some of the galaxies it photographed at the very edge of its reach were so distant, so ancient, so faint that Hubble could barely see them. Blurred smudges of light at the outer limits of its vision. What were those objects exactly? What did they look like up close? What was happening inside them? And what came before them? What existed in the time before even those early galaxies had formed? Those questions needed a new instrument. They needed Webb. It took decades to design, decades more to build and test. Engineers had to solve problems that had never been solved before. How do you build a mirror 6.5 meters wide and then fold it up small enough to fit inside a rocket, only to unfold it perfectly in the cold of space, hundreds of thousands of kilometers from Earth, with no possibility of a repair mission if something went wrong? How do you keep the telescope cold enough, colder than 150 degrees below 0 Celsius, so that its own heat doesn't contaminate the faint infrared signals it's trying to detect? How do you point it with sufficient precision that it can hold steady on a target for hours at a time, drifting by no more than the width of a human hair as seen from 2 kilometers away? These were not small engineering challenges. Each one required years of thought and testing and iteration. Each one was, in its own way, a kind of miracle of human ingenuity. And on Christmas Day, 2021, the telescope launched from a spaceport on the northeastern coast of South America, folded like an origami crane inside its rocket fairing. Over the following weeks, it unfolded itself, one painstaking step at a time, as mission controllers on Earth held their breath. Every deployment had to work, every hinge, every latch, every motor, and one by one, they did. The mirror opened. The sunshield, a 5-layered structure the size of a tennis court, designed to keep the telescope perpetually in shadow, deployed without incident. Webb cooled to its operating temperature. Its instruments came online, and it began to see. Webb doesn't just extend Hubble's legacy, it honors it. Every image Webb sends back, every ancient galaxy, every stellar nursery, every exoplanet atmosphere, carries with it the accumulated effort of all the scientists and engineers and dreamers who came before, of all the people who looked up at the night sky and asked, what else is out there? The answer, it turns out, is more than we ever imagined. And so tonight, as you rest, as your body settles and your thoughts begin to soften at the edges, there is a golden mirror, 1.5 million kilometers away, turning its gaze toward the oldest light in the universe. It is patient in a way that we rarely get to be. It does not tire. It does not wonder if it's doing the right thing. It simply looks and listens and gathers photons that have been traveling since before the Earth was formed. And we, here, get to be the ones who asked it to look. That's enough for now. Rest easy. We have 5 more acts to go, and there is no hurry at all. Act 2. Build to see the invisible. If you've ever stood outside on a clear night and looked up at the stars, you've seen the universe the way human eyes were built to see it. Invisible light. The warm yellow glow of distant suns. The cold blue shimmer of stars burning hotter than our own. The faint smear of the Milky Way arching overhead. Millions of stars blurring together into something that looks almost like a cloud. It's beautiful, it's humbling, and it's also, in a very real sense, incomplete, because the universe does not communicate only in visible light. Visible light, the light our eyes can detect, the light that fills our days and lets us see the faces of the people we love, is just one narrow band in an enormous spectrum of electromagnetic radiation. On one side of it sits ultraviolet light, and beyond that, X-rays, and beyond that, gamma rays. On the other side sits infrared light, heat radiation, and beyond that, microwaves, and beyond that, radio waves. All of these are light in the physical sense. They are all the same kind of wave, differing only in their wavelength, the distance between the peaks of the wave as it travels through space. Our eyes evolved to detect a very specific range of those wavelengths, the range that the sun happens to emit most abundantly. But the rest of the spectrum exists whether we can see it or not. And much of what the universe most wants to tell us, much of what Webb was built to hear, is written not in visible light, but in infrared. Tonight, let's talk about how Webb was designed to read it. The James Webb Space Telescope observes the universe across a wavelength range of approximately 0.6 to 28.5 micrometers. A micrometer is 1/1,000,000th of a meter. So we're talking about wavelengths that are almost impossibly small by everyday standards, but within that range lies almost the entire infrared spectrum, stretching from the near infrared, which sits just at the edge of what human eyes can almost but not quite perceive, all the way out into the mid-infrared, deep into territory our senses have no tools to access at all. To understand why that matters, it helps to think about 2 things: dust and distance. First, dust. Space is not as empty as it looks. Between the stars, and especially inside the great clouds of gas and dust where stars are born, there are vast quantities of microscopic particles, grains of carbon, silicates, ice. These particles are so small that a single one is invisible to the naked eye, but in the aggregate, across distances of light years, they form clouds so thick that they block visible light entirely. The great stellar nurseries of our galaxy, the Eagle Nebula, the Carina Nebula, the Orion molecular cloud, are beautiful in visible light, but the visible light only shows us their surfaces. The actual process of star formation is happening deep inside, hidden behind walls of dust that no optical telescope can penetrate. Infrared light passes through that dust, the way a radio signal passes through walls. The wavelengths are long enough that the dust particles simply cannot block them. The waves flow around the particles and continue on their way. When Webb turns its gaze on a stellar nursery, it doesn't see the surface. It sees through the surface. It sees inside. It sees the young stars in the earliest moments of their lives, still wrapped in the cocoons of dust and gas from which they formed. Objects that have never been seen before, because no instrument capable of detecting them at this resolution has ever existed until now. This alone would make Webb extraordinary. But then there's the second reason infrared matters: distance. You may have heard of something called the Doppler effect. It's the reason an ambulance siren sounds higher pitched as it approaches you and lower pitched as it moves away. The sound waves are compressed in front of the moving source and stretched out behind it. Light behaves the same way. Objects moving away from us have their light stretched to longer wavelengths, and because the universe is expanding, because every galaxy is moving away from every other galaxy, carried apart by the expansion of space itself, the most distant objects in the universe have their light stretched the most. The galaxies of the cosmic dawn, the first galaxies that formed after the Big Bang, are so far away and moving away from us so rapidly that the visible light they emitted over 13 billion years ago has been stretched by the time it reaches us, all the way out of the visible spectrum and into the infrared. If you were to look at those galaxies with an optical telescope, you would see nothing. Not because there is nothing there, but because the light they emitted is no longer the kind of light an optical telescope can detect. Webb can detect it. Its range of 0.6 to 28.5 micrometers is not an arbitrary specification. It was chosen with great deliberation, tuned specifically to the wavelengths, where the oldest and most distant light in the universe now resides. Every time Webb looks at one of those ancient, faint, red-shifted galaxies, every time it brings into focus something that no human eye has ever seen, it is doing so because engineers sat down decades ago and asked, what range of wavelengths do we need to cover, and how do we build an instrument capable of covering them? And then they built it. There is something quietly moving about that. The light from the cosmic dawn has been traveling for over 13 billion years, crossing an almost incomprehensible distance, stretching and reddening as it goes. And at the end of that journey, it finds a mirror waiting for it. A mirror we put there because we wanted to see where it came from. Let that thought accompany you a little way into the night. That mirror, the great golden structure at the heart of the James Webb Space Telescope, is one of the most precisely engineered objects ever created by human hands. It measures 6.5 meters across. As we touched on in Act 1, that's large enough to dwarf Hubble's mirror many times over in light collecting area. But the size alone doesn't capture what makes it remarkable. What makes it remarkable is how it was made, and why it looks the way it does. The mirror is not a single piece. It is made up of 18 individual hexagonal segments, each one about 1.32 meters from edge to edge, arranged together like a honeycomb to form the full aperture. Each segment is made from beryllium, a lightweight, rigid metal chosen because it maintains its shape even at the extraordinary temperatures Webb operates at, temperatures far colder than anything that exists naturally on Earth. But beryllium alone would not be enough. To reflect infrared light effectively, a mirror must have an extremely smooth, highly reflective surface. And beryllium, while structurally excellent, is not naturally the ideal reflective material for the infrared spectrum. So each of the 18 segments was coated with a microscopically thin layer of gold. Gold. Not for beauty, though the result is undeniably beautiful. Those photographs of the fully deployed mirror, gleaming in the light of the clean room where it was assembled, have become some of the most visually striking images in the history of space exploration. The gold was chosen for a purely scientific reason. It is an exceptionally efficient reflector of infrared light. Gold reflects infrared radiation at roughly 98 to 99% efficiency, losing almost nothing of the precious signal it collects. Every photon that strikes the mirror needs to be directed onward to Webb's instruments as faithfully as possible. And gold does that better in this wavelength range than almost any other material. The layer of gold on each segment is extraordinarily thin, about 100 nanometers, 100 billionths of a meter, so thin that the entire gold coating of all 18 segments combined weighs less than 50 grams. Less than a small chocolate bar. That thin film of gold, spread across 6.5 meters of mirror, is enough. But collecting light is only part of the challenge. The mirror also has to be pointed with extraordinary precision. Each of the 18 segments can be adjusted individually, moved by tiny actuators, motorized mechanisms that can position each segment to within a fraction of a wavelength of light. After launch, and after the mirror unfolded itself in the cold of space, engineers spent months carefully aligning all 18 segments until they functioned not as 18 separate mirrors, but as one single, unified, optically perfect surface. It is worth pausing here to appreciate the audacity of this. 18 separate pieces, built on Earth, folded up, launched into space on top of a rocket, unfolded in the cold and vacuum 1.5 million kilometers from home, and then aligned remotely to tolerances measured in fractions of a wavelength of light. The engineers who designed this system had to trust completely in the precision of every component, the reliability of every motor, the correctness of every calculation. There was no room for error, and there was no way to send someone out to fix it if something went wrong. But it worked. When the first test images came back, images used to check the alignment of the mirror before science operations began, engineers and scientists who had spent years, in some cases decades, working on this telescope reportedly wept when they saw them. Not because they were unexpected, but because they were perfect. Because the mirror had opened exactly as designed, aligned exactly as planned, and was showing them the universe with a clarity and depth that, even after all those years of work, was still breathtaking to actually see. There is a particular kind of emotion that comes from watching something you've worked very hard on finally do exactly what you hoped it would. Even if you've run the simulations 1,000 times, even if you were confident it would work. Seeing it actually work, seeing the light actually arrive, seeing the image actually form, is something else entirely. The scientists who built Webb know that feeling, and now, in a quieter way, so can we. The universe speaks in wavelengths we were not born to hear. It hides its oldest light behind curtains of dust and distance, stretching and shifting it into a register that no unaided human sense could ever detect. So we built an ear. We built an eye. We coated 18 pieces of beryllium in a whisper-thin layer of gold, and we sent it 1.5 million kilometers from home, and we opened it up in the dark. And it listened. Now, so can you. Let the edges of the day soften. Let the details blur a little. There is more to come, but there is no hurry. The telescope is still out there, still watching, still gathering a light that has traveled longer than the Earth has existed. Rest easy. Act 3 is waiting whenever you're ready. Act 3. The cold, dark observatory in space. There is a place in space, not marked by anything visible, not distinguished by any physical feature you could point to, where the gravitational pull of the Earth and the gravitational pull of the Sun balance each other so precisely that an object placed there will stay there, orbiting the Sun at exactly the same rate the Earth does, always keeping pace, never drifting ahead and never falling behind. It has a name. Mathematicians and astronomers call it the second Lagrange point, or L2. It sits about 1.5 million kilometers directly behind the Earth, on the side facing away from the Sun, so that if you were standing there, looking back, you would see the Earth and the Sun lined up together. The Earth, a small blue marble hanging in front of the Sun's vast, burning face. L2 is not a place humanity has ever visited. No human spacecraft has ever carried a person there. It is far too distant, more than 4 times farther than the Moon, well beyond any crewed mission we have ever flown. But it is, for reasons we'll explore in this act, just about the perfect place in the solar system to put a telescope like Webb. Let's talk about why. The James Webb Space Telescope orbits the Sun at the L2 Lagrange point, approximately 1.5 million kilometers from Earth. 1.5 million kilometers. It is a number large enough to feel abstract, so let's try to feel it a different way. Light, the fastest thing in the universe, travels at roughly 300,000 kilometers per second. A signal sent from Earth to Webb, traveling at the speed of light, takes about 5 seconds to arrive. That's not long by the standards of deep space communication, but it is long enough that Webb is genuinely, meaningfully alone out there. Not in radio contact with us the way a passing satellite would be, not visible from the ground with any backyard telescope, just quietly present in a region of space that no human hand will touch for the foreseeable future. The choice of L2 was not accidental, and it wasn't purely about the gravitational convenience of staying in one place without constant fuel expenditure. It was about something more fundamental: darkness. At L2, Webb sits in a unique geometry relative to the Sun, the Earth, and the Moon. All three of those objects, the three brightest, warmest things in Webb's vicinity, are located in roughly the same direction from the telescope's perspective. They are all, more or less, in front of it. This means that with a single large shield positioned between the telescope and that direction, Webb can block the light and heat from all three simultaneously. This matters enormously, for reasons we'll come to shortly. But first, consider the elegance of the arrangement. By choosing L2, engineers didn't just find a gravitationally convenient parking spot. They found a location where the geometry of the solar system itself cooperates with the telescope's mission, where the Sun, the Earth, and the Moon are all conveniently gathered on one side, leaving the other side in perpetual uninterrupted darkness. Webb hovers at that point like a figure standing just inside a doorway, looking out into the night. The warmth and light are behind it. The cold and dark are ahead, and in that cold and dark, it can see things that would be invisible anywhere else. There is something almost meditative about it. 1.5 million kilometers from the nearest person, from the nearest voice, from the nearest sign of life, sitting in absolute silence, turning its golden mirror toward the oldest light in the universe. It keeps its vigil without complaint, without fatigue, without the need for anything we could give it, save for the occasional command sent at the speed of light across the dark, to protect itself from the warmth of the Sun, the Earth, and the Moon. The James Webb Space Telescope carries with it one of the most remarkable engineering structures ever sent into space: a 5-layered sunshield, roughly the size of a tennis court. Stretched to its full extent, the sunshield measures approximately 21 meters by 14 meters, longer than a school bus, wider than most houses. It is made from a material called Captain, a thin, lightweight polyamide film that can withstand extreme temperatures on both its sun-facing and space-facing sides without degrading or tearing. Each of the 5 layers is coated with aluminum, and the 2 sun-facing layers are additionally coated with silicon to reflect and emit as much of the sun's heat as possible. The 5 layers are not stacked tightly together. They are separated by gaps, each layer slightly smaller than the one below, arranged in a precise geometric sequence. This matters because heat management in space is not simply a matter of blocking radiation. It is about carefully controlling how that radiation is absorbed, reflected, and re-emitted. Each layer of the sunshield intercepts some of the incoming heat and radiates it away sideways into space before it can reach the next layer. By the time you work through all 5 layers, the temperature reduction is extraordinary. The sun-facing side of the sunshield, the side pointing toward the Sun, the Earth, and the Moon, reaches temperatures of roughly 85 degrees Celsius, hot enough to boil water in other circumstances, hot enough that you would not want to touch it. And on the other side, just a few meters away, separated by those 5 thin layers of coated film and the vacuum gaps between them, the temperature is negative 233 degrees Celsius. That number deserves a moment. Negative 233 degrees Celsius, absolute zero, the coldest temperature theoretically possible, the point at which all atomic motion ceases, is negative 273 degrees Celsius. Webb's cold side sits just 40 degrees above that absolute limit. In the entire universe, the only places colder than the back of Webb's sunshield are the deepest reaches of intergalactic space, far from any star. The sunshield, folded like a delicate origami structure inside the rocket fairing at launch, unfolded itself over the course of about 8 days after Webb left Earth. It was one of the most tense periods of the mission. The sunshield alone required 107 individual release mechanisms to deploy correctly. 107 separate mechanisms, every one of which had to work in the right sequence, in the cold and vacuum of space with no possibility of manual intervention. 107 things that had to go right, they all did. When the last layer of the sunshield finally tensioned into place, flight controllers at the Space Telescope Science Institute exhaled in collective relief. The hardest part of the deployment was over. The telescope was beginning to become, out there in the dark, what it had been designed to be. The temperature difference created by the sunshield, that vast quiet gulf between 85 degrees on the hot side and negative 233 on the cold, is not merely a side effect of the telescope's design, it is the whole point. Webb's scientific instruments, in order to detect the faint infrared light they were built to see, must themselves be extraordinarily cold. This is because infrared detection is, at its heart, the detection of heat, of thermal radiation. Any warm object emits infrared radiation simply by virtue of being warm, which means that if Webb's instruments were even slightly warm, they would be flooded with their own thermal noise, unable to distinguish the faint signal of an ancient distant galaxy from the infrared glow of their own components. To do their job, Webb's instruments must be cooled to temperatures where they themselves emit almost no infrared radiation at all. The near-infrared instruments, the ones that look at wavelengths just beyond what human eyes can see, operate at around negative 233 degrees Celsius, cooled passively by the sunshield. They require no active refrigeration. The sunshield does the work simply by blocking the sun's warmth so completely that the instruments cool themselves, radiating their own tiny amount of heat away into the empty space behind them until they reach equilibrium at temperatures that would be difficult to achieve even in the most advanced laboratory on Earth. And then there is MIRI, the mid-infrared instrument, which observes the longest wavelengths in Webb's range, the deep mid-infrared where the most ancient and most heavily redshifted light resides. MIRI operates at negative 266 degrees Celsius, just 7 degrees above absolute zero. To achieve this, it uses a cryocooler, an active refrigeration system powered by electricity that continuously pumps heat away from the instrument and radiates it into space, 7 degrees above absolute zero. There is almost nothing in the natural universe that cold. The cosmic microwave background, the faint glow left over from the Big Bang itself, pervading all of space in every direction, has a temperature of about negative 270 degrees. MIRI operates at a temperature colder than almost everything in the observable universe, except that primal afterglow. And it needs to be that cold, because the light it is trying to detect is so faint, so tenuous, so whisper-quiet after its journey of 13 billion years, that the slightest warmth in the instrument would drown it out completely. The universe is trying to send us a message written in the faintest possible ink, and Webb has made itself as quiet and still as anything can be, so it can read it. Think about that as you settle in. Somewhere out there, 7 degrees above the coldest temperature that physics allows, a detector is listening, waiting for light that left its source before our star was born, counting photons, one by one, from the edge of time, and each night that passes on Earth, Webb is still there, still cold, still watching, still listening to the universe tell its oldest story, the cold, the dark, the distance. These are not obstacles Webb endures. They are conditions it was designed to inhabit. It sought them out. It traveled 1.5 million kilometers to find a place where the geometry of the solar system would cooperate, where a thin folded shield could create a pocket of near absolute zero cold in which the faintest light in the universe could finally, after 13 billion years of traveling, be heard. There is a kind of peace in that, if you let yourself feel it. The universe is vast and ancient and mostly cold and mostly dark. And somewhere in all of that, a small golden mirror is waiting, with perfect patience, to catch what's been traveling toward it since before the Earth existed. You can let your own thoughts grow quiet now. The telescope doesn't need anything from you tonight. It's already doing what it was made to do. Act 4 is waiting, gently, whenever you return. Act 4, Launch Day and the Great Unfolding. Every great journey has a moment of no return. A door that once walked through cannot be reopened. For the James Webb Space Telescope, that moment came on the morning of December the 25th, 2021, when the engines of an Ariane 5 rocket ignited on a launch pad on the northeastern coast of South America, and everything that 25 years of work had been building toward was committed irrevocably to the outcome. Before we talk about that morning, before we talk about the weeks that followed, and the astonishing, nerve-wracking process of unfolding a telescope in the cold of space, it's worth stepping back and appreciating just how many hands built the thing that sat on that launch pad. Because Webb did not belong to any single nation or any single space agency. It was, from the very beginning, a shared endeavor. The James Webb Space Telescope is the product of an international partnership between 3 space agencies: NASA, the American space agency that led the mission, ESA, the European Space Agency, and CSA, the Canadian Space Agency. It is, in the truest sense, a telescope that belongs to the world. NASA's contribution was the largest: the overall mission architecture, the primary mirror, the spacecraft bus, and 2 of the 4 main scientific instruments. But the European and Canadian contributions were not merely symbolic. ESA provided the rocket, the Ariane 5, one of the most reliable heavy-lift launch vehicles ever built, and contributed one of Webb's 4 instruments, a spectrograph called NIRSpec, capable of measuring the chemical fingerprints of up to 100 objects simultaneously, analyzing the light from distant galaxies and parsing it into its component wavelengths the way a prism splits white light into a rainbow. Canada contributed the fine guidance sensor, which allows Webb to lock onto a target with almost incomprehensible precision, and a near-infrared imaging instrument called NIRIS. Together, these agencies pooled not just their funding and their hardware, but their expertise, engineers and scientists from across Europe and North America working in concert over more than 2 decades, across time zones and languages and institutional cultures, toward a single shared goal. There's something quietly hopeful about that. Space exploration, at its best, has always had this quality: the capacity to draw people together across borders, to find common cause in the shared project of understanding where we come from and what we are. Webb represents that quality in its most realized form. It is a machine of uncommon ambition, built by uncommon cooperation. The rocket that carried it, ESA's Ariane 5, launching from the Guyana Space Center in Kourou, French Guiana, was itself the culmination of decades of European aerospace engineering. Ariane 5 had by that point conducted more than 100 launches, with an exceptional record of reliability. It was chosen not just for its payload capacity, but for that reliability. When you're launching the most complex and expensive scientific instrument ever built, an instrument with no possibility of repair, you want the most dependable rocket available. The launch occurred on Christmas Day, 2021, at 7:20 in the morning local time in Kourou, which was 12:20 in the afternoon in London and just after midnight on the west coast of North America. Across the world, people who had followed Webb's long development, scientists, engineers, and curious onlookers who had simply heard about this extraordinary machine, watched live streams and held their breath. The launch itself went beautifully. Ariane 5 lifted off cleanly. The first stage separation occurred on schedule, and approximately 27 minutes after liftoff, Webb separated from the upper stage of the rocket and began its independent journey through space. But the launch was only the beginning of the precision required. Webb did not travel to L2 in a straight line. No spacecraft ever does. Getting to L2 requires a carefully calculated trajectory, a long curving arc through space, and along that arc, Webb performed a series of small engine burns called mid-course corrections. These were not emergency maneuvers, they were planned from the beginning, built into the mission design, each one calculated to nudge Webb's trajectory just slightly, accounting for the tiny but real differences between where the rocket aimed and where physics actually delivered it. The first mid-course correction burn happened just 12.5 hours after launch. It lasted less than a minute, but it was critical. It set the baseline for the trajectory that would carry Webb the rest of the way. Subsequent burns refined the path further. Together, they guided Webb toward L2 with a precision that, from a distance of 1.5 million kilometers, amounts to threading a needle. There is a particular kind of quiet anxiety that mission controllers live with during this phase. Not dramatic alarm, but a sustained, low-level vigilance, checking and rechecking the numbers, watching the telemetry, confirming that the spacecraft is doing what the models predict. For the most part, Webb did exactly that. Each correction, burn performed as expected. The trajectory held. The James Webb Space Telescope, for all its physical scale, that 6.5-meter mirror, that tennis court-sized sunshield, those 4 complex scientific instruments, launched with a mass of approximately 6,200 kilograms, around 6 metric tons. That is large by the standards of scientific spacecraft. But here is the surprising thing. The Hubble Space Telescope, launched in 1990, had a launch mass of roughly 11,000 kilograms, nearly twice as heavy as Webb. How is it possible that a telescope with a mirror more than 6 times larger in collecting area, with more advanced instruments, and a vastly more complex deployable structure, weighs less than half of what Hubble did at launch? The answer lies in material science and in the demands of the mission. Hubble was designed to be serviced by astronauts in low Earth orbit. It was built robustly, with the expectation that human hands would periodically open it up, replace components, and upgrade its instruments. That robustness has mass. Webb, by contrast, was always going to be unreachable once deployed. There would be no servicing missions, so every gram mattered in a way it hadn't for Hubble. Engineers use beryllium for the mirror segments, lighter than glass and structurally superior at cryogenic temperatures. They use Kapton film for the sunshield, rather than rigid panels. They push the limits of lightweight engineering at every turn, shaving mass wherever they could without compromising performance. The result is a telescope that is, in a sense, exactly as heavy as it needs to be, and not a gram more. There is a particular engineering elegance in that, in the discipline of building something that does more while weighing less. Webb did not simply fire its engines and coast to L2. The trajectory that carried it there was carefully designed to take advantage of the gravitational geometry of the Earth-Sun system, and to preserve as much of Webb's onboard propellant as possible. The spacecraft carries a finite amount of fuel for its thrusters. That fuel is used not just for the journey to L2, but for the station-keeping maneuvers that will keep Webb in its orbit around L2 for the duration of its operational life. Every gram of propellant spent unnecessarily during the journey is a gram unavailable for later use. And less propellant means a shorter mission life. The launch vehicle itself contributed significantly here. The Ariane 5 rocket delivered Webb to its initial trajectory with such precision, better, in fact, than the minimum required, that Webb needed to spend less propellant than planned on its first mid-course correction. Mission planners, doing the math in the days after launch, realized that the accuracy of the Ariane 5's delivery had effectively given Webb a gift: more fuel in reserve than the baseline mission plan had assumed. More fuel means a longer mission. The original design lifetime for Webb was 10 years. With the extra propellant, scientists and mission planners revised their estimates upward. Webb, they concluded, likely had enough fuel for significantly more than 20 years of operations, more than double the original expectation. A Christmas launch, a Christmas gift, in more ways than one. Webb arrived at L two-folded. This is perhaps the most important engineering fact about the telescope, the one that, more than any other, defines the character of the mission and the nature of the risk involved in getting it there. The Ariane 5 rocket's payload fairing, the nose cone that protects the spacecraft during launch, is approximately 5 meters in diameter and about 17 meters tall. The James Webb Space Telescope, fully deployed, is roughly 20 meters across and 14 meters tall. It does not fit, not even close. So Webb was folded. The primary mirror, those 18 hexagonal gold segments, was folded in 3 sections. The central 12 segments plus 2 outer wings, each wing hinged and folded back against the central structure like the pages of a book closing. The sunshield, that tennis court-sized structure, was pleated and folded and rolled and bundled into a compact package, secured with those 107 release mechanisms we mentioned in Act 3. The secondary mirror, which sits in front of the primary on a tripod-like structure and redirects the collected light back into the telescope's instruments, was folded down flat against the primary mirror assembly. Everything that needed to be large, everything that was required to be large to do the science, had to first be made small. Small enough to fit inside a fairing, small enough to survive the vibration and acoustic forces of launch without damage. Small enough, and yet precisely designed, so that when the time came to unfold, every hinge and latch and motor would function exactly as intended, in the cold and vacuum of space without anyone nearby to check. The engineers who designed the system knew, with full clarity, what they were asking of themselves and of the hardware. They knew that a single failed deployment mechanism could compromise the mission entirely. They designed around that knowledge, testing each mechanism thousands of times on the ground, building redundancy wherever possible, and then, ultimately, accepting that there are some risks that cannot be eliminated, only managed and minimized. They managed and minimized them well. The deployment of the James Webb Space Telescope unfolded over 2 weeks after launch, a sustained, choreographed sequence of events that mission controllers managed one careful step at a time. On December 28th, 3 days after launch, the aft momentum flap, a small fixed panel that helps stabilize the spacecraft against the gentle pressure of sunlight, was released and locked into position. A small step, but the first of many. On December 31st, New Year's Eve, the sunshield pallets unfolded. The 2 structures that hold the sunshield membranes in place were rotated out to their operating positions. Then, over the following days, the sunshield membranes themselves began to deploy. The forward and aft unitized pallet structures opened. The mid-booms, long telescoping booms that pulled the sunshield layers out to their full width, extended. And the 5 layers of the sunshield were separated and tensioned, one by one, until they were stretched taut in the configuration they would hold for the rest of the mission. January 5th, 2022, 12 days after launch, was the day the secondary mirror deployed. Swinging out from its folded position against the primary mirror to the end of its tripod structure, where it needed to be. The secondary mirror is small, just 74 centimeters in diameter, but its position is critical. If it were misaligned by even a tiny margin, the entire optical system would be compromised. It deployed correctly. And then, on January 8th, the two wings of the primary mirror unfolded. First the port wing, then the starboard, rotating out to their operational positions and latching into place. The great golden mirror, for the first time, was fully open. It had taken 14 days. There had been moments of tension, minor anomalies, brief pauses while engineers assessed telemetry, but nothing had failed. Nothing had gone irreversibly wrong. One by one, the 344 single-point failure mechanisms that engineers had identified, the 344 things that if they failed would end or cripple the mission, had actuated correctly. All 344 of them. When the last mirror wing locked into place, the team at the Space Telescope Science Institute broke into applause. They had built this thing over decades, tested it relentlessly, worried about it in the small hours of the night, and now it was out there, fully deployed, 1.5 million kilometers from Earth, looking like the thing it had always been designed to be. The hard part was over. The best part was about to begin. There is a lesson of sorts in how Webb deployed. Not a loud lesson, not a dramatic one, but a quiet and persistent one. It unfolded one step at a time. Each small success enabled the next. No single day brought the whole telescope into being. It arrived at its final form through patience and sequencing, through trusting the process and doing the next thing and then the next thing after that. That's not a bad way to approach most things in the end. And tonight, there's nothing you need to unfold. Nothing that requires your attention or your vigilance. The telescope is already open. The mirror is already waiting. You've done enough for today. Let the rest go. Act 5 is there, quietly, when you come back to it. Act 5, turning blurry stars into a masterpiece. After the mirror wings locked into place on January 8th, 2022, it would have been tempting to imagine that the hard work was done. The telescope was open, the sunshield was taut, the instruments were powering on and beginning their slow cooling toward operating temperature. After 25 years of development and 2 weeks of white-knuckle deployment, surely the universe was ready to be observed. But the telescope wasn't ready yet, not quite. Because having 18 mirror segments open in space is not the same as having 18 mirror segments working together. Each of those hexagonal panels, each one weighing about 40 kilograms, coated in that whisper-thin layer of gold, had arrived at its operating position after being folded and launched and unfolded, and while each one was close to where it needed to be, close is not close enough for a telescope trying to resolve galaxies that are billions of light years away. Before Webb could do science, it had to be tuned. Its mirror had to be turned through a painstaking and remarkable process from 18 separate reflective surfaces into one single unified optically perfect eye. This process is called mirror alignment, and it is one of the most quietly extraordinary things that happened during Webb's commissioning, which itself was one of the most quietly extraordinary periods in the history of space exploration. In the early weeks after deployment, when engineers first turned Webb's instruments toward a bright star to test the optics, they did not see a single crisp point of light. They saw 18 of them. 18 separate images of the same star, each one formed by a different mirror segment scattered across the detector in a loose, irregular constellation. Some were brighter, some fainter, some were slightly out of focus. None of them were aligned with the others. The mirror, for all its precision engineering, was not yet a mirror in the functional sense. It was 18 separate mirrors, each doing its own thing, each pointing in a slightly different direction. The task of alignment was to take those 18 blurry, scattered images and gradually, carefully, over a period of several months, bring them together into one. Not just one image, but one perfectly coherent image, as sharp and clean as the fundamental physics of the telescope's optics would allow. The process happened in stages. First, engineers identified which of the 18 images corresponded to which of the 18 segments by deliberately tilting each segment in turn and watching which image moved. Then, they began the course alignment, using the actuators behind each segment to tilt and position them until the 18 separate images were at least roughly arranged in the right pattern. Then, they stacked the images on top of one another, bringing them into crude alignment, and then began the long, careful process of fine alignment, nudging each segment by tiny, precise amounts, checking the result, nudging again, that would eventually transform a rough stack of 18 blurry dots into a single, razor-sharp point of light. It took months. Engineers expected this. They had planned for it. The commissioning phase was always understood to be a long process, not a switch to be flipped, but a journey to be made, one careful step at a time. The patience required for this work is of a particular and unusual kind. Each adjustment has to be made, and then the telescope has to be pointed at a reference star and observed, and the data has to be analyzed before anyone can know whether the adjustment helped. There is no immediate feedback. You move the mirror, and then you wait, and then you look at the result, and then you plan the next move. It is a slow conversation between human intention and physical reality, conducted across 1.5 million kilometers of space. At a certain point during the alignment process, engineers used one of Webb's instruments in an unexpected and rather charming way. They turned NIRCam, the near-infrared camera, one of Webb's 4 main scientific instruments, around in a sense to look not outward at the universe, but backward at itself, not quite a literal about-face. But NIRCam has a feature called a pupil imaging lens, which can be inserted into the optical path to capture an image of the primary mirror itself as seen through the instrument. Engineers used this to take what became widely described, with some affection, as a selfie of the telescope. The image showed all 18 mirror segments as seen from NIRCam's perspective, bright hexagons of reflected light, the nearby equipment around them dark by contrast, each segment clearly individually visible. It was used as an engineering diagnostic tool, a way of checking the state of each segment's reflective surface, confirming that the gold coating was performing as expected, and verifying aspects of the optical alignment. But beyond its technical purpose, the image had an effect on the people who saw it that its engineers might not have fully anticipated. Here was this telescope, this vast, complex, expensive, decades-in-the-making machine, alone in space at the gravitational balance point between the Earth and the Sun, and it had looked at itself and sent the image home. There was something almost unexpectedly human about it, something that made the telescope feel, briefly, less like an instrument and more like a presence. The image circulated widely. People who had only a vague awareness of Webb found themselves looking at it, recognizing something in it. The golden hexagons, the darkness around them, the sense of a machine quietly doing its work in an unimaginable place. It became, in a modest way, one of the iconic images of the mission. Not a scientific result, but a moment of connection between the telescope and the people who sent it there. The alignment of Webb's mirror was made possible by a system of actuators, small motorized mechanisms mounted behind each of the 18 mirror segments that could adjust the position and orientation of each segment with extraordinary precision. Each primary mirror segment sits on 6 actuators, plus one central actuator that controls its curvature. These actuators can move their segment in multiple directions, tilting it, shifting it, and in the case of the central actuator, very slightly flexing the surface of the mirror to change its focal properties. And they can do all of this with a precision measured in nanometers. A nanometer is 1/1000th of a meter. 10 hydrogen atoms laid side by side span roughly 1 nanometer. The actuators behind Webb's mirror segments can position those segments to within a few nanometers of their target position. Adjustments so small that they cannot be seen, cannot be felt, cannot be measured by any ordinary instrument. They exist in a realm of precision that is difficult to hold in the mind, because our experience of the physical world simply doesn't prepare us for it. To align an optical system at this level of precision, in space, remotely, using motors that were designed and tested on Earth and then exposed to the rigors of launch in the cold of space. This is not a routine engineering achievement. It represents decades of development in actuator technology, in metrology, in the software systems used to calculate what adjustments are needed and command them to the hardware. And yet, it worked. The actuators moved their segments to their commanded positions with nanometer level accuracy. The mirror came into alignment. Physics cooperated with engineering, as it does when the engineering is done carefully enough. There is a kind of faith involved in this, actually. You design the actuators, you test them, you do the calculations, and then you launch them into space and command them to make adjustments you cannot directly verify until you look at a star and see how the image has changed. At every step, you are trusting that what you built and tested on the ground will behave the same way in the cold and vacuum of space. Webb's actuators justify the trust completely. When Webb's alignment was complete, when all 18 segments were working together as a single unified mirror, the images it produced had a characteristic appearance that any astronomer who has seen them now recognizes immediately. Stars in Webb's images don't look quite like stars in Hubble's images, or stars in images from ground-based telescopes. They have a signature quality, instantly identifiable, that is a direct consequence of Webb's mirror geometry. They have spikes. Each bright star in a Webb image is surrounded by a pattern of diffraction spikes, long, sharp rays of light extending outward from the central point, like the spokes of a wheel or the rays of a drawn sun. Most telescopes produce 2 or 4 diffraction spikes from the struts that hold the secondary mirror in place. Webb produces 8. The reason is the hexagonal geometry of the mirror segments. When light reflects off a mirror made of hexagons arranged in a honeycomb pattern, the edges of those hexagons interact with the light in a specific way, creating a diffraction pattern with 6-fold symmetry. And Webb's particular arrangement of 18 hexagons, with its 3-fold structure, produces the distinctive 8-spike pattern seen in its images. 2 spikes from the secondary mirror support struts, 6 from the mirror geometry, 8 in total. Engineers knew this would happen. It was calculated before the telescope was built. The spikes are not a flaw. They are a predictable consequence of the physics of diffraction, and they carry no scientific drawback. The spikes appear around bright stars, but the vast majority of the objects Webb is interested in, galaxies, nebulae, exoplanet systems, are not affected by them, and for the stars that do produce spikes, the pattern is so precisely understood that it can be accounted for in data analysis. But beyond the science, the spikes have become something else. They have become Webb's visual signature. They are the mark by which a Webb image is instantly recognized. When you see those 8 rays of light spreading out from a bright star against a field of galaxies, you know, without needing to read a caption, whose image this is, which telescope sent it home, which golden mirror caught the light. There is something satisfying about that, a telescope with its own unmistakable handwriting. Once alignment was complete, the full resolving power of Webb's mirror became available, and it is, by any measure, extraordinary. Resolution in telescopes, the ability to distinguish fine detail, to separate 2 close objects. that a lesser instrument would blur into one. Depends primarily on the diameter of the mirror relative to the wavelength of light being observed. Webb's 6.5-meter mirror, operating in the infrared, gives it a resolving power that in practical terms means it can detect objects of vanishingly small angular size. To give that some human meaning, if you were to take a single penny, a coin about 19 millimeters across, and place it approximately 40 kilometers away, the angular size of that penny at that distance is roughly what Webb can resolve at its sharpest. A penny, 40 kilometers away. Or think of it this way. When Webb looks at a cluster of galaxies many hundreds of millions of light years distant, it can resolve individual stars within those galaxies. Not just the smear of combined light, but distinct points corresponding to individual suns, each of them perhaps larger than our own. Stars that are not merely far away, but cosmically far away, separated from us by distances that make the already incomprehensible distance to L2 seem like a step across a room. This resolution is what allows Webb to do science that was simply not possible before it existed. It is what allows it to study the structure of early galaxies, not just detect them as faint blobs of light, but examine their shapes, their star-forming regions, their central cores. It is what allows it to look at a planet orbiting another star and measure, in some cases, the chemical composition of that planet's atmosphere. It is what allows it to peer into the dusty heart of a stellar nursery and see the individual young stars forming within. All of that resolving power lives in the curvature of those 18 gold segments, now aligned to within nanometers of each other, working together as one. Months of careful work, countless small adjustments, an almost meditative process of refinement, of getting closer and closer to perfect, in a place where no one could directly observe what was happening, and every result had to be inferred from the data that came back across 1.5 million kilometers of silence. And at the end of it, a mirror. One mirror made of 18, tuned to see the universe as clearly as the laws of physics allow. There's something in the commissioning of Webb that mirrors, and perhaps that word is apt, the way most meaningful things come together. Not all at once, not in a single moment of revelation, but gradually, through patient effort, through incremental improvement, through the willingness to look at the current result and ask what small adjustment might bring it slightly closer to what you hoped for. The universe doesn't reveal itself all at once, neither does sleep, most nights. It comes in layers, in small surrenders, in the gradual loosening of the day's grip on the mind. Let the next layer come. The telescope is sharp now, so the universe is in focus. You can look whenever you're ready. And if you're not ready, if sleep has already found you, that's exactly right. Act 6 is there, in the morning or the night after or whenever you return. It will wait. Act 6, the science era. Everything before this moment, the decades of design, the international partnerships, the Christmas morning launch, the 2 weeks of white-knuckle deployment, the months of patient mirror alignment, all of it was preparation. All of it was the long walk to the door. This is what's behind the door. The science era of the James Webb Space Telescope began in earnest in the summer of 2022, when the first full-resolution science images were released to the world. And in the time since, Webb has done something that the best telescopes in history have always done. It has answered questions, and in doing so, it has raised more questions than it answered. It has confirmed some of what we expected to find, and surprised us with things we did not expect at all. Tonight, in this final act, we'll visit some of what Webb has found. Not all of it. The list grows every month, and no single evening could hold it. But enough to give you a sense of the scope and the texture of what this telescope is telling us or about the universe we live in. Let these discoveries wash over you gently. Some of them are small and precise. Some of them are large and unsettling in the best possible way. all of them are real. Among Webb's 4 scientific instruments, NIRSPEC, the near-infrared spectrograph contributed by the European Space Agency, has a capability that sounds almost too convenient to be true. It can observe more than 100 different objects simultaneously. A spectrograph works by splitting the light from an object into its component wavelengths, the way a prism splits white light into a rainbow. That spectrum is a fingerprint. Every element, every molecule, every chemical compound absorbs and emits light at specific characteristic wavelengths, a pattern as distinctive as a barcode. By reading the spectrum of a distant galaxy, you can determine what it's made of, how fast it's moving, how hot its stars are, whether it contains gas that suggests active star formation or a quiet old age. Spectrographs have existed for as long as modern astronomy, but traditionally they work on one object at a time. You point the telescope, you take the spectrum, you move to the next object. For a telescope as capable as Webb, observing one object at a time for the kind of survey science that requires thousands of spectra would take a prohibitively long time. NIRSPEC solves this with a device called a microshutter array, a grid of 250,000 individually controllable tiny shutters, each one smaller than a human hair is wide. By opening specific combinations of shutters, NIRSPEC can simultaneously collect the spectra of more than 100 objects scattered across a patch of sky, each one feeding its light through its own dedicated shutter into the instrument's detectors. In a single observation, NIRSPEC can do what would once have required 100 separate pointings. This is how Webb conducts large-scale surveys of distant galaxies, sweeping up spectra by the hundreds, building statistical samples that allow astronomers to understand not just individual objects, but populations of objects, trends across cosmic time, the broad sweep of how galaxies form and evolve. One instrument, one exposure, 100 stories, told simultaneously in light. Beyond the deep universe, Webb turns its gaze closer to home, or at least to the neighborhoods of other stars. It is one of the most powerful tools yet devised for the study of exoplanets, worlds orbiting other suns, some of which may bear conditions not entirely unlike our own. The technique Webb uses most powerfully for this is called transit spectroscopy. When a planet passes in front of its host star, as seen from Webb's position, a small fraction of the starlight filters through the planet's atmosphere, if it has one, before reaching the telescope's detectors. Different molecules in that atmosphere absorb different wavelengths of light. By carefully comparing the spectrum of the star when the planet is not transiting with the spectrum when it is, astronomers can identify the specific wavelengths that have been absorbed, and from those absorptions, deduce what molecules are present in the planet's air. It is, in its way, an almost impossibly delicate measurement. The signal is tiny. The atmosphere of even a large exoplanet contributes only a tiny fraction of the total light being observed. But Webb's mirror is large enough, and its instrument sensitive enough to detect those tiny signals with confidence. This capability was one of the key reasons Webb was built. The question of whether other planets have atmospheres, and what those atmospheres contain, is not just a scientific question. It bears directly on one of the oldest and most profound questions humanity has ever asked, and Webb is, right now, actively pursuing the answer. In the first year of science operations, Webb used transit spectroscopy to make a landmark observation of a planet called WASP-39b. This is a large, hot gas giant, roughly the mass of Saturn, orbiting very close to its star, completing an orbit in just over 4 Earth days. It is emphatically not the kind of place where life as we know it could exist, but it is exactly the kind of place where Webb's atmospheric capabilities can be demonstrated and tested. And the results were remarkable. In a single set of observations, Webb's instruments detected carbon dioxide in WSP-39b's atmosphere, the first unambiguous detection of carbon dioxide on a planet outside our solar system. Beyond carbon dioxide, the data revealed sulfur dioxide, water vapor, sodium, and potassium. It showed evidence of photochemistry, chemical reactions driven by the star's radiation, happening in real time in the planet's upper atmosphere. And subtle features in the spectrum offered hints about how the planet formed and migrated to its current position so close to its star. Each of these detections, individually, would have been a significant result. Together, they amounted to the most detailed chemical portrait of an exoplanet atmosphere ever assembled, and they were obtained in a small fraction of the time that would have been required by any previous instrument. WASP-39b is not Earth-like, but the techniques proven on it will be applied to smaller, cooler, potentially habitable worlds in the years ahead. Webb is learning to read atmospheres. What it finds when it reads the right ones, nobody yet knows. Closer to home, within our own galaxy, Webb has revisited objects that previous telescopes had studied and found things that were hidden. The Southern Ring Nebula is a planetary nebula, the glowing shell of gas expelled by a dying star, slowly expanding outward into space over thousands of years. It has been observed many times. It is well studied. Hubble photographed it. But when Webb looked at the Southern Ring Nebula, it saw through the dust and gas in a way no previous telescope could, and it revealed something that had been invisible before. At the center of the nebula, where astronomers had known there were two stars, Webb's infrared vision showed that one of those stars was surrounded by a disk of dust. That dust disk told a story. The two central stars had been interacting as one of them died, exchanging mass. The surviving star's disk shaped and fed by the interaction. The nebula's complex asymmetric structure, the way the expelled gas had spread in certain directions more than others, was the fingerprint of that ancient interaction between two stars in a slow gravitational dance. Without Webb, that dust disk would have remained hidden. The story of how the nebula came to look the way it does would have stayed unread. Webb didn't just image the nebula, it explained it. In another corner of our galaxy, Webb turned its gaze toward a system called WR140, a binary star system containing a Wolf-Rayet star, one of the most massive and luminous types of stars known, burning so hot and so intensely that it sheds its outer layers in a powerful stellar wind. What Webb found there was breathtaking in the most literal sense of that word. The two stars in WR140 orbit each other on an elliptical path. Every 8 years, they swing close together. And when they do, the stellar winds from both stars collide at a high speed. In the turbulent zone where those winds meet, dust forms, and as the stars then swing apart again and the dust expands outward into space, it forms a shell, a ring of dust centered in the binary system. This has been happening every 8 years for a very long time, and Webb imaged the result, 17 concentric rings of dust, nested inside each other like the rings of a tree, each one representing a single close passage of the two stars 8 years apart. The outermost ring was formed roughly 130 years ago. The innermost was more recent. It is a clock, a record of 17 orbits written in dust, expanding outward into space. And Webb is the first telescope able to see it clearly. There is something almost impossibly elegant about it. The universe keeping its own careful record in expanding shells of dust, waiting for an instrument sensitive enough to read them. Webb has also turned its eyes to one of the most dramatic events in the nearby universe, the collision of two galaxies known as the Antennae galaxies, a pair of spiral galaxies in the slow billion-year process of merging. Galaxy collisions are among the most energetic events in the cosmos, but they proceed on timescales so vast that from our perspective they appear frozen, a snapshot of violence caught mid-frame. The antennae have been studied for decades. Their long tidal tails of stars, the antennae that give the pair their name, are visible in optical images. But the regions of active star formation within the collision zone were largely hidden behind dense clouds of dust. Webb pierced that dust, and in doing so, it revealed hundreds of previously invisible young star clusters, dense knots of newly formed stars, still wrapped in the dusty cocoons from which they had so recently emerged. These clusters are the direct product of the collision. When the two galaxies' gas clouds crashed together, the shock compressed the gas to densities high enough to trigger star formation on a massive scale. Webb can see those newborn stars in their nurseries, measure their ages, trace the progression of star formation through the collision. What was once a beautiful but partially obscured image of cosmic violence is now a map of creation. Among the surprises Webb has delivered, one of the more unexpected concerns dust, specifically how much of it existed in the very early universe. Cosmic dust, the microscopic grains of carbon and silicates and other materials that pervade galaxies and nebulae, is not primordial. It forms primarily in the envelopes of dying stars, in supernova remnants, and in various other processes that require stars to have lived and died. The conventional wisdom held that the early universe, not yet old enough for many generations of stars to have formed and died, should contain relatively little dust. Webb has found galaxies in the early universe that are far dustier than models predicted. Galaxies seen as they were just a few 100 million years after the Big Bang. Galaxies that, by any prior reckoning, shouldn't yet have had time to make much dust, are producing and containing dust in quantities that challenge the standard picture of early galaxy evolution. This means either that dust forms faster than we thought, or through processes we hadn't fully accounted for, or that early galaxies evolved more rapidly than our models had assumed. Probably some combination of all three. Webb hasn't yet resolved the question, but it has sharpened it considerably, and pointed the way toward a revision of our understanding of how the first generations of galaxies build themselves. When Webb began its deep surveys of the early universe, staring at patches of sky for many hours at a time, collecting the faintest possible signals from the most distant possible sources, one of the first things it did was find galaxies at redshifts higher than had ever been confirmed before. Redshift, as we discussed in Act 2, is the stretching of light by the expansion of the universe. The higher the redshift, the more the light has been stretched, and the farther back in time the source sits. A redshift of 10 means we are seeing a galaxy as it existed roughly 13 billion years ago. A redshift of 13 means we are looking even further back, to within the first few 100 million years after the Big Bang. In its first year of science operations, Webb detected and confirmed galaxies at redshifts above 13. It detected candidates at even higher redshifts. It pushed back the confirmed frontier of galaxy observation further than any previous instrument, finding galaxies that formed earlier and that were, in some cases, more massive and more fully developed than models of early galaxy formation had predicted. The universe, it seems, got to work faster than we thought. Galaxies assembled themselves, grew massive, and began forming stars earlier in cosmic history than the standard models had anticipated. Webb is not overturning our understanding of the Big Bang or of cosmic evolution, but it is adding detail and nuance and correction that will take years of the theoretical work to fully absorb. Among the unexpected discoveries of Webb's early science years, a class of objects has emerged that nobody predicted with any specificity. Astronomers have taken to calling them, with characteristic dry affection, the little red dots. They appear in Webb's deep field images as small, compact, distinctly reddish sources, objects that, when their spectra are analyzed, turn out to be at very high redshifts, meaning they're extremely distant and therefore very early in cosmic history. Their red color is partly a consequence of that distance, but also partly intrinsic. Something about these objects makes them red, even accounting for redshift. The leading interpretation is that the little red dots are the compact, active cores of early galaxies, regions where supermassive black holes are actively consuming surrounding material and radiating enormous amounts of energy. In other words, they may be a previously unidentified population of early active galactic nuclei. Black holes in the act of growing, caught in a phase of their evolution that we hadn't anticipated finding in such numbers or at such early times. They are not fully understood. Papers continue to be written about them. The theoretical community is actively debating their nature and their implications. Webb has handed astronomers a new puzzle, gift wrapped in faint red light from the early universe. The little red dots connect to a broader and more fundamental puzzle that Webb has helped to sharpen: the question of how supermassive black holes got so big, so fast. Supermassive black holes, the kind that sit at the centers of most large galaxies, with masses millions or billions of times that of our Sun, are ubiquitous in the nearby universe. The Milky Way has one. Virtually every large galaxy we can study in detail has one, but growing a black hole to those masses takes time. Black holes grow by accreting mass, swallowing surrounding gas and stars, and this process has physical limits, known as the Eddington limit, on how fast it can proceed. The problem is that Webb keeps finding supermassive black holes that are too massive, too early. Galaxies in the young universe, galaxies seen as they were just a few 100 million years after the Big Bang, are hosting black holes that should not, by conventional models of black hole growth, have had time to reach those masses. The universe simply hasn't been around long enough, by those models, for the black holes to have eaten their way to that size. Something is wrong with the models, or something about early black hole growth is different from what we assumed. Perhaps early black holes grew from more massive seeds than we thought. Perhaps the Eddington limit can be exceeded under certain conditions. Perhaps some other process we haven't accounted for is at work. Webb has not yet answered the question, but it has posed it more insistently than any previous telescope, and in doing so, it has set in motion a generation of theoretical work that will reshape our understanding of how the universe's largest structures came to be. In 2024, Webb observed what became, at the time of its confirmation, the most distant galaxy ever spectroscopically confirmed. Its designation is JWST 14-0, a name that only an astronomer could love, but which carries within it the coordinates of its discovery in the JD survey and the redshift that places it at the very edge of the observable universe. JADES-GS-Z14-0 is seen as it existed just 290 million years after the Big Bang. It is a young galaxy by any measure, but it is not a small or simple one. It is already luminous, already massive, already, in Webb's data, showing signs of significant stellar populations. And in its spectrum, Webb detected something that raised eyebrows across the astronomical community: nitrogen. Specifically, a spectral emission line associated with nitrogen in an ionized state, glowing in the ultraviolet light of the galaxy's hot young stars. Nitrogen is not a primordial element. Like carbon, like oxygen, like most of the elements heavier than hydrogen and helium, nitrogen is forged in the cores of stars and released into the interstellar medium when those stars die. For a galaxy seen just 290 million years after the Big Bang, to already contain detectable nitrogen means that at least one generation of stars, and possibly more, had already formed, lived out their lives, and died within that galaxy before Webb observed it. Stars had already been born and had already returned their chemical products to the interstellar medium, enriching the galaxy's gas with elements that only stellar nucleosynthesis can produce. 290 million years after the Big Bang, that is, by cosmic standards, almost no time at all, and yet stars had already been born and died. The universe did not ease into existence. It hit the ground running, and Webb is showing us, in detail, just how fast it ran. 11 discoveries, and these are only a handful, a carefully chosen sample from a catalog that grows with every passing week, every new observation, every new dataset released to the astronomical community around the world. Webb is not finished. It is not slowing down. Every night that passes on Earth, the telescope at L2 is completing another exposure, collecting another spectrum, catching another handful of photons that have traveled for 1 billion or 10 billion or 13 billion years to fall upon its golden mirror. The science era of the James Webb Space Telescope has barely begun. Epilogue: how long this story can run. If you're still here, if sleep hasn't yet found you, or if you've surfaced briefly from its edges and drifted back to these words, then we've arrived together at the end, or what passes for an end. Because one of the things about the James Webb Space Telescope is that its story doesn't have a clean conclusion. Not yet. Perhaps not for a very long time. Let's talk about how long. When Webb launched on Christmas morning 2021, its design specification called for a mission lifetime of 10 years. 10 years of science. 10 years of looking back toward the cosmic dawn, of reading exoplanet atmospheres, of piercing the dust veils around newborn stars. 10 years was what engineers planned for, what scientists built their research programs around, what funding agencies justified their investment against. 10 years was the promise, and it was a good promise, enough time to accomplish extraordinary things. But the universe, it seems, had other ideas. Or rather, the Ariane 5 rocket did. As we touched on in Act 4, the delivery of Webb to its initial trajectory was more accurate than required. The rocket aimed true. It placed Webb so precisely on its intended path that the mid-course correction burns, the carefully rationed engine firings needed to nudge the spacecraft toward L2, required less propellant than the mission plans had conservatively assumed. Propellant, for a spacecraft like Webb, is life. It is used not just for the journey to L2, but for the station-keeping burns that will keep Webb in its halo orbit around the L2 point for as long as the mission runs. Halo orbits are not perfectly stable. They require periodic small corrections to maintain. Without those corrections, Webb would slowly drift away from L2 and eventually be unable to maintain the geometry needed to operate its sunshield and point its instruments. When the propellant runs out, the mission ends. And so, in the days after launch, as mission planners did the accounting, tallying what had been used, what remained, what the station-keeping burns were expected to cost per year, they found themselves looking at numbers that were better than they had dared to hope. The propellant reserve was larger than the baseline mission had assumed. The revised estimates, released publicly in early 2022, suggested that Webb had enough propellant for significantly more than 20 years of operations. Some analysis pointed toward lifetimes approaching or exceeding 25 years, depending on how carefully the propellant is rationed and how stable the halo orbit proves to be in practice. 20 years, perhaps more. Where Webb was promised 10, it may deliver 20. Where 10 years of discoveries were expected, the universe may receive 20 or more. Years of that golden mirror catching light that has traveled since before the Earth existed. Think about what 20 years means in the context of what Webb has already done in just its first 2 or 3 years of science operations. In its first year, it confirmed the most distant galaxy ever observed. It detected carbon dioxide on a planet orbiting another star. It revealed the dust disk around the dying star at the center of the southern ring Nebula. It found the little red dots. It began to stress test our models of early black hole growth. In its second and third years, it has gone further still, into more distant galaxies, into more complex exoplanet atmospheres, into the fine chemical detail of objects like JWST 14-0 and its unexpected nitrogen. And that is just the beginning of a mission that may have 18 or 20 years left to run. The discoveries Webb will make in year 10, let alone year 20, cannot be predicted. That is the nature of genuine scientific exploration. You build the instrument, you point it at the universe, and the universe shows you things you didn't know to look for. Every great observatory in history has surprised its builders. Hubble was supposed to resolve a long-standing debate about the expansion rate of the universe, and it did that. But it also revealed that the expansion is accelerating, a discovery so unexpected and so consequential that it earned a Nobel Prize and introduced the concept of dark energy into our scientific vocabulary. Nobody planned for that. Nobody could have. Webb will have its own equivalents, results that nobody planned for, questions that nobody thought to ask before Webb showed them something that made the question necessary, discoveries that will reshape our understanding in ways that we cannot, from where we sit tonight, anticipate. And somewhere in those future results, in year 7 or year 14 or year 19, there may be something that changes everything. Some observation that, like the accelerating expansion of the universe, requires us to revise not just a parameter in a model, but a fundamental assumption about how the cosmos works. Or perhaps not. Perhaps the next 20 years will be a steady, cumulative deepening of what we already know, less dramatic in any single moment, but no less profound in its totality. An atlas of the early universe, built one exposure at a time. A chemical survey of hundreds of exoplanet atmospheres. A complete accounting of how galaxies form and die across cosmic time. Either way, Webb will be out there, still cold, still watching, still catching the light that the universe has been sending toward us since long before we existed to receive it. And that perhaps is the most remarkable fact of all. Not any particular discovery, not any specific number, not the 6.5 meter mirror, not the 28.5 micrometers of wavelength range, not the negative 266 degrees Celsius of MIRI's operating temperature, not the 344 single-point failure mechanisms, all of which worked, not the 107 release mechanisms of the sunshield, all of which opened, not the 1.5 million kilometers of distance, not the 25 years of development, not the Christmas Day launch. The most remarkable fact is simpler than any of those. It is this: we wanted to see the beginning of the universe, and so we built something that could. We're a species that has existed in our current form for perhaps 300,000 years, the blink of an eye against the 13 billion year history of the cosmos. We live on a small rocky planet orbiting an unremarkable star in the outer reaches of an ordinary galaxy. We are made of atoms forged in stellar furnaces, assembled by evolution into bodies that are fragile and brief and finite in an every measurable way. And yet, we looked up. We asked where all of this came from. We weren't satisfied with not knowing, and we decided, collectively, over decades, across national borders and institutional rivalries and the ordinary human difficulties of any large cooperative endeavor, to build a machine capable of looking back to the very beginning. And we did it. The machine works, the light is arriving, the universe is telling its oldest story, and for the first time in 13 billion years of that story being in existence, there is someone here to listen. That is who we are, when we are at our best. So tonight, as you rest, As your body settles and your breathing deepens and the day releases its hold on you, let that be the thought that carries you the rest of the way into sleep. Somewhere out there, 1.5 million kilometers from here, a golden mirror is open in the dark. It is cold and still and patient in a way that nothing alive can be. And it is looking, on your behalf and on behalf of everyone who has ever looked up at the night sky and wondered at the oldest light in the universe. It will still be looking when you wake up. Rest now. The universe isn't going anywhere, and neither is the telescope.